All right. Greetings, YouTube. Beautiful mind here. Let's see. So this takes us into, this is what, week 6, Monday? All right, so a few announcements. So I think exam 3 has been up since about last week. It's due this Saturday, okay? Exam 3 is up. It should be up. It's due this Saturday at 11:59. So my intent, we're kind of approaching the home stretch, right? My intent is to get as many assignments loaded as early as possible so that you can be working on it. I really would like to go ahead and load the final exam like in the next couple of days. The final exam, I'll probably have it due at the close of class on the very last day, which is the Monday after the 16th. I'm also open to the following ideas of reducing the late penalty from 20% late penalty to 10% late penalty. So I'm open to these ideas. So I want to get as many assignments loaded, maybe even the final exam loaded, and reduce the late penalty from 20% to 10%. So what this means is that you can still submit even probably the exams. You can submit them after the fact, and you can earn up to like 90%. Right. So be on the lookout for that. I kind of want to get something like that going, just to encourage you all. So you can get, nearly any score that you want, up to like 90%. On Moodle, be sure that you've completed the participation and honesty quiz. That's very important for final submission and grades and things of that nature. Also, there's an assessment that's available on Moodle. So go to Moodle. You should see an assessment. You get one attempt at it. So when you're ready, when you feel like you're ready, that's also part of our grade as well. So just be sure to get that submitted. Okay. I can't think of anything else. So we'll take some time to continue with chapter 4. I haven't decided. I really need to. We need to at least touch on chapter 5. I think for chapter 4, I just want to go through 4:1 to maybe 4:4 or something like that. I got to look at it again. Sorry, not 4:1 to 4:4. Sorry, that's not right. But I definitely want to touch on chapter 5. I want to do a few examples from chapter 5. So somewhere in chapter 5 is where we're going to stop. I don't think we're going to do all of 5, but we'll do some of 5. So if this is week 6, I'll probably stop the last of the new material by the end of next week. Like, I don't want to do anything new beyond next week. I just want to give you some time to get your assignment submitted, go through them several times. I just want to kind of open it up, and I'm available. So the tutors should definitely be able to help you with this material. Also, I'm available. So I know the tutors are available for YouTube, for video Zoom sessions. I'm also available as well. And I also do dedicated YouTube videos walking you through the homework. If you click on the Ask My Instructor, it'll send me a screenshot of your question, and I can make a dedicated YouTube video to walk you through that question. And we can also do live Zoom sessions. Okay. All right. So let's take some time to continue chapter 4. We want to move into section 4.3, what the derivative tells us. What the derivatives tell us. So in section 4.1, we saw that the derivative is a tool for finding critical points, which are related to local max and min. As we show in this section, derivatives, first and second derivatives, tell us much more about the behavior of functions. So let's look at this idea. What do we mean by increasing and decreasing functions? We have used the terms increasing and decreasing informally in earlier sections to describe a function or its graph. For example, the graph of figure 420 rises as x increases, so the corresponding function is increasing. Figure 420 b, the graph falls as x increases, So as x increases, the y values go down. So the corresponding function is decreasing. So the following definitions makes these ideas precise. Suppose a function is defined on an interval I. We say that f is increasing on I if f of x sub 2 is greater than f of x sub 1 whenever x1 and x2 are in I and x2 is greater than x1. All right. So whenever x2 is bigger than x1, we have f of x2 is bigger than f of x1. So that's what we mean by a function is increasing. Basically, as x increases, the y increases. And conversely, we say that the function is decreasing if as the x increases, the y's decrease. Okay. So then the intervals of increase and decrease. The graph of a function gives us an idea of the intervals on which the function is increasing and decreasing, but how do we determine those intervals precisely? This question is answered by making a connection to the derivative. Recall that the derivative of a function gives us the slope of the tangent lines. If the derivative is positive on an interval, the tangent lines on the interval have a positive slope and the function is increasing on the interval. Said differently, positive derivatives on an interval imply positive rates of change, which in turn indicate an increase in function values. Similarly, if the derivative is negative, it indicates a decrease in function values. So we have this theorem 4.7. It's a test for intervals of increase and decrease. Suppose f is continuous on the interval and differentiable at all interior points of I. If f prime is positive at all interior points of I, then f is increasing on I. If f prime is negative at all interior points of I, then f is decreasing. Okay, I'd like to just kind of work this example. So sketching a function. Sketch a graph of a function f that's continuous on all rows and satisfies the following conditions. The derivative is positive. So let's do something like this. Let me give myself some more space. Okay, so here we ask to sketch the graph of a function that's continuous on all rows and satisfies the following conditions. The derivative is positive from negative infinity to 0, 4 to 6, and 6 to infinity. Or maybe these are separate functions. These are, or we want one function or separate functions. Okay. I think it's just one function. Then the second part is that the derivative is negative from 0 to 4. The derivative f prime of 0 is undefined, and f prime of 4 is equal to f prime of 6, which is equal to 0. Okay, so let's see if we can put these notions or ideas together. So it says the derivative is positive from, let's see. So I'm gonna just do a rough sketch. Negative infinity up to 0. Let me see, then we have 4 to 6. So let's go 2, 4, 6, 8. I think that'll be good. So the derivative is positive from negative infinity to 0. So that means it's increasing over here. Let's go like this. Here's this color. So it's increasing over here. It's also increasing from 4 to 6. And it's increasing from 6 to infinity. Okay, that's fine. The derivative is negative from 0 to 4, so it's decreasing here. Let's use a different color there. So it's decreasing from 0 to 4. The derivative f prime of 0 is undefined. So that means it says, let me see, this continuous, so we don't have any holes, gaps, or breaks, but we can have a sharp corner. So I was thinking like an asymptote, but then that's gonna not make it's not gonna make it continuous. So if we wanted to be undefined, let's do a sharp, some kind of like sharp something. Let's clean it up. Something like this, all right? At 0. F prime of 4, which is equal to f prime of 6. And the derivative is going to be 0. So at 4, if it's going from decreasing to increasing, we could anticipate something like this. All right. basically where it turns from going from decreasing to increasing. Now, if we want the derivative to be 0, but it has to go from increasing to increasing at 6, we can anticipate an image kind of like this. It flattens out, and then it keeps going like that. Okay. So then if we were to put all these together like this, I would get something, I get the following kind of image. So I'm gonna go like that, I'm gonna go here. My positive x is this way, my positive y is this way. I'm gonna go 2, 4, 6. I guess we don't need to go by 2, 4. 1, 2, 3, 4, 5, 6, 7, I think will be more than enough. 1, 2, 3, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, -1, -2, -3, -4, -5, 1, 2, 3, 4. Okay. We didn't get anything about an intercept. We just needed a sharp. So at 4, it needs to be a turning point. We needed something sharp here. And at 6, it needs to flatten out. So there's increasing here. It's going this way. It flattens at 6. And it continues, something like that, right? Let's see, how do we do? So again, one possible graph, right? But the basic shape is there. Notice the sharp corner. We get a turning point when x is 4, and then we have it flattening out when x is 6. So this is similar to ours, and maybe ours is like stretched and shifted down, all right? But the gist is there. The idea is there. Okay. Let's look at this example 2. Find the intervals on which the following function is increasing, and the intervals on which the function is increasing and decreasing. Okay. So I think last time we mentioned something about finding the critical values of the function. The critical values are going to occur when the derivative is either 0 or undefined, right? So if we're doing example 2a, right? We want to find out, when is this function increasing or decreasing? So if we find those critical values, that'll give us test points. Then we just test points. We test x values. When we find the critical values, it'll break the x-axis up into sections or intervals, and then we choose test points in each interval to see if the derivative is positive or negative, right? Let's see this in action. So we have f of x equals x times e to the negative x. I want to take the derivative. Let me think something. This has a derivative of that, plus that has a derivative of that. Okay. So first let's consider f prime. Let's consider the derivative, right? So the first times the derivative of the second. So this times d by dx of e to the negative x. The first times the derivative of the second plus the second times the derivative d by dx of the first, right? So this is going to be, so the derivative of e to the negative x is itself times the derivative of negative x is -1. So this ultimately is going to be negative x e to the negative x, okay? The derivative of x is 1, so that's going to be plus e to the negative x, right? So if we want to find the critical values, if we think about the domain of e, x The domain of E is all reals. So I think we're okay there. But then let's go ahead and set this to 0. All right. So I'm going to rewrite this. Let me add a page. So these are the same as negative x plus 1 over e to the x equals 0. Right, so when is a fraction equal to 0? A fraction is equal to 0. So the critical values here are going to be, basically we set the numerator to 0 and solve, and we set the denominator to 0 and solve. Those generate the critical values. If we set the numerator to 0, and solve, we're going to get what? Negative x plus 1 equals 0. X equals 1. All right. If we set the denominator equal to 0 and solve, we have e to the x equals 0. I don't think e to the x will ever be 0, right? No matter what x you choose, it's always above the x-axis. So there's no solution there. So the only critical point is when x is equal to 1. So if that's our critical point, so what it does, if we think, well, we don't really have a sense of the graph, but you know, for instance, when x is 1, now it breaks the x-axis up into a left half and a right half, right? So if we choose a value to the left and test it, whatever, if that's going to be positive or negative, if the derivative is positive or negative on the left, it's going to be like that for the entire left-hand side, right? So a number to the left that's easy to choose is 0. We're going to plug that into the derivative. Let me redraw this prime, right? This is the derivative. So when we plug 0 into the derivative, okay, if we say f prime is 0, that's going to be what? Negative 0 plus 1 over e to the power of 0. Okay. So what is this going to be? 1 over 1, which is just 1, right? Which is positive. The main thing is that that's positive. So to the left, let me make a note like this. So on the left-hand side, f prime of x, they're all going to be positive, right? To the left of 1. So let's test a number to the right of 1. And here, just to be a little bit more, so we know style. That is associated with that. And we'll do the right-hand side. We'll use green. So we'll do f prime of 2, since that's to the right of 1. Give me a moment. And we're back. I had to sneeze and I didn't want to like blow up the microphone, blow out your ear. Okay, so the derivative, we're going to say negative 2 plus 1. Negative 2 plus 1 to the power of e squared. Let's see, that's going to be negative 1 over e squared, which is going to be a negative number divided by a positive number, which is ultimately a negative number, right? So everything to the right of 1 is, let me see, so f prime of x over here is going to be less than 0. So our claim is that the original function is increasing. So our claim is that f of x is increasing from negative infinity up to 1 like this. And we're also claiming that f of x is decreasing from 1 to infinity like this. Like my spacing is like totally off. All right. So these are the results that I got. Let's see, how do we do? Let's see, did we answer the question? Find the intervals on which the following functions are increasing and decreasing. Okay, so that was example 2, part A. I'm gonna just let that be and sit for a moment, and I'm gonna go ahead and do part B. Part B, our function is, we have f of x equals 2x cubed plus 3x squared plus 1. Let me cut that. This is going to be example 2b. Okay. So if we want to find out when is this function increasing, decreasing, and constant, okay. So does this, can you get a sense of what this graph might look like from college algebra, right? Notice that the highest exponent, what's the highest exponent here? Is a degree 3 polynomial. So what that means is that the long-term behavior goes in opposite directions. Because the leading coefficient is positive, we would anticipate the right-hand side to go up, the left-hand side to go down. We have a y-intercept of 1. So we might have 2 turning points. So we're kind of anticipating an image that looks something like the following. I'll do it in like this color, right? Let's do, so this is an initial glance. Because it's a degree 3 polynomial. The leading coefficient is positive, implies that the right-hand side goes up, left-hand side goes down. The y-intercept is 1, so it crosses the y-axis here. And so we might anticipate something that might behave something of this nature. Nope. We're not solving for any real intercepts, but just basically something that kind of behaves like that. Something like this, right? So where we have we're anticipating 2 turning points. Now we can do a further analysis to get more accurate, but let's go ahead and find those turning points and talk about, and we can have, it looks like we have two intervals where it's increasing and 1 interval where it's decreasing. All right, let's see if we can find this. Okay, so, and again, this is just an estimate or a rough sketch of what we're anticipating. This isn't anything, so I'm gonna just shrink that down. Okay, so if the original is this 2x cubed plus 3x squared plus 1, let's look at the derivative. F prime of x. If we take the derivative, 3 times 2 is 6x squared plus 6x. I think that's it, right? So if we set it to 0, we can factor out a 6x. We're going to be left with x plus 1 equals 0. 0 factor property, 2 things multiply to give us 0. Either the first thing equals 0 or the second thing equals 0. So then from the first one, we get that x equals 0 or x equals -1, right? Okay. So these are critical points that we would have to test. So now, so what these do, it takes the x-axis and breaks it up into 3 sections. We have here where x is 0, here where x is, here, let me see, here is when x is -1, here's where x is 0. Okay. These make f prime, make the derivative 0, okay? So let's choose a number to the left of -1 to test. So we'll look at when x is -2, all right? F prime. Did I do f prime in the last one too? It should be f prime, right? So 6x squared, so that's gonna be 6 times -2 squared plus 6 times -2. 4 times 6 is 24. Minus 12 is a positive 12. So it's positive over there. Okay, between -1 and 0, we're going to do f prime of -1/2. 6 times -1/2 squared plus 6 times a -1/2. That's going to be a 1/4, so that's 3/2. That's going to be what? -3, which is going to be a -3/2, which is negative. Okay. And then to the right of 0, let's test 1. So we're going to do f prime of 1. It's going to be 6 times 1 squared plus 6 times 1. It's ultimately going to be 12, which is positive. So here we're saying f prime of x was positive, so we expect it to be going up. Here, f prime of x, let me write this a little bit better. F prime of x was positive, so we anticipate something like this. Here, f prime of x was negative, so we expect it to be decreasing. And here, f prime of x was positive, so we expect it to be increasing. So it is kind of following that pattern, okay? So our claim is that the original function is, let's see, f of x is increasing from negative infinity up to negative 1 and from 0 to infinity. And then our claim is that f of x is decreasing from negative 1 to 0. Okay. Let's see, how do we do? So for the first one, it says it's increasing from negative infinity to 1, and then it's decreasing from 1 to infinity. Let me see how we're doing that first one. Yep. And then the second one, increasing from negative infinity to negative 1, decreasing from negative 1 to 0, and then increasing from 0 to infinity. Okay? All right. Let's keep it going. So we saw a demo on using the first derivative to identify when a function is increasing, decreasing, or constant, essentially. A function is increasing when the derivative for all those values are positive. The function is decreasing when the derivative for all the values is negative, right? So if we can use the derivative to identify increasing, decreasing, and constant, we also know that, you know, the derivative being 0 means that the slope of the tangent line is 0, and that usually occurs at like a turning point or a critical point. Okay. Let's see. I just want to see. I think we have this first derivative test. Let's look at this, right? So notice that, like at the local max and the mins, the derivative is 0. Now the derivative being 0 doesn't guarantee a turning point, but if we can show that on either side of the turning point that it goes from increasing to decreasing or vice versa, that implies that it could be another candidate. Let's see. So we have the first derivative test. Assume f is continuous on an interval and that assume f is continuous on an interval that contains a critical point c, and assume that f is differentiable on an interval containing c, except perhaps at c itself. If f prime changes sign from positive to negative as x increases through c, then f has a local max. So it goes from positive to negative, so from increasing to decreasing. And conversely, if it goes from decreasing to increasing, then we have a local minimum. If f prime is positive on both sides near c are both negative, then f has no local extrema value at c. I just want to look at this example. Find the intervals on which this is increasing and those on which it's decreasing, and then identify the local extrema. Okay, all right. Should already have a page, so I'm gonna just do this. Okay. So let's see, this is what, example 3. We have this f of x equals 3x to the 4 minus 4x cubed minus 6x squared plus 12x plus 1. All right. So we want to find where it's increasing and decreasing, and find a local extrema. Okay. So basically, let's take a look at the derivative and set it to 0. We're going to get 12x cubed. 4 times 3 is 12. X squared. 6 times 2 is 12. X plus 12. So many 12s. All right. If we set this to 0, notice we can factor out a 12. So we're going to get 12 times, we're going to have, I'm just going to divide both sides by 12. We get this x cubed minus x squared minus x plus 1 equals 0. Let's see, can we factor this? I'm going to do factor by grouping, right? So if we look at the first two, we can factor out what? X squared. What's left is x minus 1. Let's factor out a negative 1 from the second two terms, and we're going to be left with x minus 1. All right. So now we can factor out that common binomial factor. They both have the x minus 1, and we're left with x squared minus 1 equals 0. Now we have difference of squares, so this is going to ultimately become x minus 1. That's going to be x minus 1 times x plus 1 equal to 0. Okay. So we need to test, what is it, when x is 1 and negative 1. So here's our negative 1, here's our 1. We want to look at the derivative. Where's our f prime? All of this is, okay? I think I might put that 12 back. I hadn't decided yet. Yeah, I think it's okay. And we'll do like this. Okay. Yeah, it keeps irking me, so I'm just gonna I'm gonna leave this 12 there like this. I'm gonna just leave it 12, and I'll just there. It's not really anything. I'm just gonna leave it there just for my own sake, my own peace. Okay, so if this is the derivative, we want to test like 3 test points, right? So let's do f prime of negative 2. So let's see, that's going to basically be 12 times negative 3 times negative 3 times negative 2 is negative 1. So ultimately this is going to be negative. So to the left of negative 1, the function should be decreasing. Between negative 1 and 1, let's look at f prime of 0. That's going to be 12 times negative 1 times negative 1 times 1. Double negative is ultimately going to be positive. Let's do f prime of 2. So it should be increasing here. It's going to be 12 times 1 times 1 times 3. This also positive. So it should be increasing over here as well. So it looks like we will only have one local extrema when x is negative 1. Okay, let's get some more space or paper. So then if when x is -1, that's going to be a local extrema. Let's find out what that point is. Let's do f of -1. So if we do f of -1, I need this guy. Let's just copy, paste. So there's going to be 3 times -1 to the 4 minus 4 times -1 cubed minus 6 times -1 squared, 12 times -1 plus 1. Okay. So that's going to be 3 plus 4 minus 6 minus 12 plus 1. Let's see, 7 minus 6 is 1. That's a -11, -10. Okay. So, and notice that it's going from decreasing to increasing. So we're saying that we have a local minima of -10 at x equals -1. So we have this as a result. And then from part A, so we said the function, I need some more space. Let's go like this. So we said the function f is decreasing from -infinity up to -1, and we said f is increasing from -1 to 1 and from 1 to infinity. Okay. All right, let's see how do we do. So for part A, well, okay, I'm just going to go with it. So what we have, I was trying to get the articulation. That's why I was kind of hesitating. But it's okay. And then part B, let's look at part B. So f of -1 to give us -10. So we only have the local minimum value of -10 when x is -1. Okay, I think we got that one. Okay. Oh. What's the time? Okay, we're okay. All right. Oh, so in example 4, we're asked to find the local extrema of this function. Okay, let's do it. Paper. So let's see, for example 4, we have g of x equals x to the 2/3 times 2 minus x, all right? So then we want to look at g prime of x equal to, so the first, which is this guy, times the derivative of that, which is just going to be what, -1, plus the second, which is this guy, times the derivative of the first, which is going to be 2/3 x to the -1/3. Okay. Let's see, that's in the denominator. So if we set this equal to 0, well, first, if that it's going to be undefined when x is 0 because we have that negative exponent, so that's in the denominator. So cube root is 0, right? Okay. So we want one critical value is when x is 0. Now, if we set this to 0, let's see. Can we factor? Okay. So this is, let's see. We have this negative x to the 2/3 plus 2 minus x over x to the 1/3, right? And we have all of this equal to 0. So we can get a common denominator of x to the 3rd, right? 3x to the 3rd. So we're going to multiply that left one by 3x to the 3rd on top and bottom. So then what we'll get is -3x. On the right, we're going to have 4. We're going to have 4 minus 2x, okay? And this is going to be all over 3x to the 3rd. And we have this equal to 0. So then it looks like we get -5x plus 4 over 3x to the 3rd equals 0. That 3x to the 3rd, that's where the 0 comes from that we got earlier. If we set the numerator to 0 and solve, we have this -5x plus 4 equal to 0. Subtract 5x equals -4, divide x equals 4 by 5. So then we want to test 0 and 4 by 5. So if we look at the derivative f prime of -1, the number to the left is 0. Sorry, g. Got a common denominator. I'm just making sure that that's still my derivative at the end. Okay. So then we're going to get this -5 times -1 plus 4 over 3 times -1 to the 3rd. So that's going to be, 9 over, that's going to be a -1, that's going to be -3. This is ultimately -3, which is negative. So it's going to be f prime of x is negative here, so it should be decreasing. Between 0 and 4/5, I'm going to do a half. So I'm going to do g prime of 1/2. Let's see, that's going to be, do we have any, maybe a 9th? Maybe an 8th. Anyway, let's just keep going with this. So this is going to be -5 times 1/2 plus 4 over 3 times 1/2 to the 1/3, right? It's going to be a negative 2.5. So it's ultimately going to be a positive number on top. Cube root of a half is still going to be positive, and a positive number on bottom, which is positive, right? So we'd anticipate the original graph to be increasing on this interval. A number to the right of 4/5, I'm going to choose 1. So we're going to look at g prime of 1. That's going to be the negative 5 times 1 plus 4 over 3 times 1 to the third. 3 times 1 to the 1/3. The top is going to be negative. The bottom is going to be positive. So this is ultimately negative. So it should be decreasing to the right. Okay. Let's go back to the original question. So it looks like we have local extrema when x is 0 and x is 4/5, right? So we need to calculate g of 0, and we need to calculate g of 4/5. So then g is here. Let me just get a copy of this. Okay. So then if we do g of 0, did we say? I feel like there's something I'm missing, but let's keep going. So we have a 0 to the 2/3 times 2 minus 0. I think it's just going to be 0, right? So that's the origin. We have what? A local minimum. So we have a local min value of 0 at x equal to 0, right? And then let's do when x is equal to 4/5. So then we got this one. And then what it is. Let's do g of 4/5. So then g of 4/5 is going to be 4/5 to the power of 2/3. 2 minus, is it 2? 2 minus 4/5. Let's see, cube root, it's going to be positive. Squared is going to be positive, and that's positive. So this is ultimately going to be positive. Oh, wait. We don't want positive. We want the actual number. All right, this is probably going to be some decimal. Let me find that decimal. So divided by 5. Use my calculator. Okay, reload, refresh. Okay. So I'm just going to do 4/5 to the power of 2/3 times 2 minus 4/5. Okay, I think this is okay. I get about 1.03. I feel like I made a mistake. 1.03, but let's just keep going with it. It's approximately 1.03. And we're saying that that's a local max value. So we have a local maximum value of approximately 1.03 at x equals to 4/5. Okay. Let's see, how do we do? All right. So min and a max. Let's see, how do we do? What did you take that away from? I see it. Let's take you and put you where you need to go. Cut. Paste. Okay. G prime of x, 4 minus 5x divided by 3 times x to the third. Okay, so we got that. Okay. I'm just trying to read it. Let's see. Okay, local minimum at 0. Local max at 4/5. 4, 3, 1. Local max and a local min. Okay. Okay. I see the time. Let's keep going. We're almost there. We're almost done with the slides that I have prepared. Okay. So I think we're okay with what we got. So we have this extreme, absolute extreme values. Okay. So one local extremum implies absolute extremum. Suppose f is continuous on an interval that contains exactly one local extremum. If a local maximum occurs at c, then f of c is the absolute maximum on that interval. If a local minimum occurs at c, then f of c is going to be the absolute minimum on that interval. Verify that this has an absolute extreme value on its domain, x to the power of x. Okay, so let me see. Okay, let's go like this. Paper, that's fine. Actually, we need this because I remember this one from last time, and I think it was something different for me. I think I had experienced something like this a long time ago, and I completely forgot about it. And a long time ago, I did not know how to do it. I got stuck. But then after we talked about it last class, I saw the technique that they used, right? So it says, verify that this has an absolute extreme on its domain. Okay. So this is example 5. And we have f of x equals x to the power of x. Okay. So note that f of x equal to x to the power of x. We can rewrite this as e to the power of the log of x to the x, because we're using the property of inverses, right? So then we can rewrite this as e to the power of x natural log of x. That's the property of the log of a power becomes the power times the log. Okay. And I think in this form we can now take the derivative. So if we look at f prime of x, that's going to be itself e x log of x times the derivative of the exponent. So if we do the exponent, the first times the derivative of the second, which is going to be 1 over x, plus the second times the derivative of the first, which is just 1. Okay. So then here, let's see. So here we get x to the power of x times 1 plus the natural log of x. Okay. This is f prime. So then we want to set it to 0. So then either x 0 to the power of 0, so it's not going to be defined there, right? Or is it just going to be 0? It should be undefined when x is 0. Let me see. 0 to the 0. All of those are 0, but I think 0 to the 0 is undefined. Yeah. If you think about the graph. Okay. So critical values are when x is 0. So what we would have to do, like if we set this equal to 0, but this is undefined for x equal to 0. So critical number is going to be x equal to 0. I don't want you to think that 0 is coming from there. That was just undefined. I'm going to get rid of that. But I'm saying x equal to 0 is a critical number because 0 to the 0 is undefined, right? Because the exponential function, power functions, 0, no. 0 to the power of 0. Yeah, the base has to be for exponential functions, the base has to be positive numbers not equal to 1, right? So I mean, long story short, we're saying that a critical number is going to be x equal to 0, and then we have the other one is that 1 plus the natural log of x. We also have to set that equal to 0. Okay. Let's keep it going. So if we solve, we subtract the natural log of x equals -1. So then x is going to be e to the power of -1, right? So critical numbers, 2 point something, so like almost like near a little smaller than a half. So we want to test when x is 0 and test when x is e to the -1. Okay. F prime of x. So my f prime is here. Let me copy this. Okay. So let's test to the left of 0. Let's do f prime of -1. It's going to be -1 to the -1. 1 plus the log of -1. Okay. So -1 to the -1 means what? 1 over -1. So that's ultimately just going to be -1 times. Can we take the log of negatives? I don't think so. No, we can't, right? That's undefined. So that makes all of this. Okay. Let me go back then. Let me go back and figure out this key right here. Now we have e to the power of x log x, right? So the log of x, that domain is restricted to positive x, right? X can't be negative. So instead of x equals to 0, x is supposed to be strictly larger than 0. So I don't know that we can do that. Strictly larger than 0. So we're only going to test, we're only going to have the e to the -1. I'm going to get rid of all of this. Okay. Delete. Get rid of this guy as well. X has to be strictly larger than 0. Okay. So then here, I should have kept, do I still have that copy, paste? So we're going to say f prime of x is going to be this. So if we're going to say f prime of, now e to the -1, I think it's about like a half, it's a decimal, less than 1. So I'm going to choose something like 1 or 2. Because if e is 2 point something, when you do 1 over, it makes it less than 1. So then when we do f prime of e to the -1, that's going to be, man, that's a lot going on. E to the -1, that's just a number, to the power of e to the -1. Again, just that same number times, oh, sorry, we want something to the right. I'm totally tripping. All right, let's try this again. So, and let's not do e to there. We want to do, so let's choose something like 1, right? So 1 to the 1 times 1 plus the natural log of 1. Natural log of 1 is what? 0. So ultimately this is just 1, which is positive. So it should be increasing. What about to the left of this guy? So I think a number to the left, because we said it has to be strictly larger than 0. Ooh. 1/3. So let's do 1/4. So we do have to kind of go from 0 off to the right. Let's do f prime. Let's do f prime of 1/4, 1/4. That should be a number to the left of e to the -1, right? Let's just give it a go. So 1/4 to the power of 1/4. So that's like the 4th root of a positive is positive. Times 1 plus the natural log of 1/4. That's going to be negative, right? So then we're going to have a positive, the natural log of 1/4, natural log of 4. It's going to be negative. Log of 0. I was trying to do this in my head, and I think I'm getting like sleepy. Let me just pull up my calculator and crunch that number. I think it should be a negative though. So I'm going to do this. Clear. I'm going to say 1/4 to the power of 1/4 times 1 plus the natural log of 1/4. I think that's ultimately going to be negative. It is negative. Okay. Yeah. So I just did it in my calculator, and this was ultimately a negative number. Okay. So on the left of this, it was decreasing. On the right, it was increasing. So we should have a local minimum. So we have a local min value of, so now we got to plug in e to the -1 into f of x. Almost there. Oh, f of x is x to the x. Okay. So if we do f of e to the minus 1. This is going to be e to the minus 1 to the e to the minus 1. Let me see something. I just try to see if I can do this without my calculator. E to the minus 1. That minus 1 is going to go there. 1 over e to the minus 1. Okay. I'm just going to use my calculator for that last part. It should be positive. So I'm just going to put e to the minus 1 to the power of e to the minus 1, double close. Let's see what happens. We get about 70. It's approximately 0.6922. So we have a local minimum value of 0.6922 at x equals e to the minus 1. And let's just find out what the e to the minus 1 is. Second e to the minus 1. 3679. This is approximately 3679. Okay, let's see how do we do. Okay. So we said it went from decreasing to increasing. Okay. What number was that? Thank goodness that was 5. Okay. First note that it's continuous on 0 to infinity because x to the, okay, right here. X to the x is equal to e to the x natural log of x. So then we have the derivative. Solving is a single critical point, e to the minus 1. There is no point in the domain in which f prime does not exist. The critical point splits the domain into the intervals. It's negative and it's positive. First derivative of local minimum. Approximately 0.69. Okay. That was an adventure. Whew. All right. Let's see. Concavity and inflection points. Okay, I'm just going to look at the, because I'm kind of, see, we don't really have a lot more time, but we're also almost done with these slides. So concavity. Let f be differentiable on an open interval. If f prime is increasing, then f is concave up. If f prime is decreasing, then it's concave down. If f is continuous at c and f changes concavity from up to down, then we call that an inflection point. Okay, if f prime is increasing, so that's usually concavity is a discussion centered around the second derivative, right? So again, not f prime being positive or negative, but the derivative of the derivative. So f prime being increasing or decreasing, right? So we have this test for concavity. Suppose the second derivative exists. If the second derivative is positive, then we say that the function is concave up. If the second derivative is negative, we're going to say that the original function is concave down. Okay, I'm going to let those be. Let me see. I think we have a total of 8 examples. Sketch a function satisfying each of the conditions. I'm going to leave this one as an exercise just for the sake of time. I'm going to get rid of that page. Yeah, I'm just going to leave that as an exercise. That's fine. I'll leave it as is. Identify the intervals in which the function is concave up or concave down, and then find the inflection points. I'm just going to do one of these because we're about out of time, and I'm kind of tired. All right. So let's do example 7. Okay. Let's do 7a. We have this f of x equals 3x to the 4 minus 4x cubed minus 6x squared plus, isn't this one we did earlier? So then the first derivative was 12x cubed minus 12x squared minus 12x plus 12. So if we want concave up, we want to find out when is the derivative increasing or decreasing. So in other words, look at the second derivative, f double prime of x. What is that? 36x squared minus 24x minus 12. We want to set this equal to 0 and solve. We can factor out what? 12 from everything. So this would be 12 times 3x squared minus 2x minus 1. Okay. Two numbers that multiply to give us -3 and add to give us -2. Okay. -3 and 1. Okay. So we're going to rewrite this 2 as -3x plus 1x. Yeah, I'm gonna just use the box method. I don't know, I'm partial to the box method. Nah, it's fine. We can just keep going factor by grouping, right? So then the 12 is gonna come down. We could factor out a 3x from the first two terms. And we're gonna be left with x minus 1 plus another x minus 1. Okay. It's equal to 0. So then we'll get, if we factor out the common binomial factor, which is the green part in this case, 12 times x minus 1, 3x plus 1 equal to 0. Okay. So then from here, we get that what? X equals 1 or x equals a -1/3. This is the second derivative, right? So these are potential candidates for the inflection point. So here is our -1/3. Here's our +1. To the left, let's see, if we did f double prime of -1, that's to the left of -3. That's going to be 12 times -2. -3 plus 1 is -2. It's going to be 4, which is positive. So it's going to be positive over here. So our claim is that the function is concave up over here. All right. Okay. Between -1/3 and 1, I'm going to do f double prime of 0. That's going to be 12 times -1 times +1, which is ultimately negative. So our claim is that the function is concave down over here. To the right of 1, I'm going to do f double prime of 2. F double prime of 2 is going to be what? 12 times 2 minus 1 is 1. 6 plus 1 is 7. Notice that these are ultimately positive. Concave up, right? Okay, so if we have these x values, we need to go back and find the corresponding y's from the original. Ugh, I'm going to use my calculator for sure on this one. Let's copy. Add a page. And let's paste. Okay, so the first one was a f of negative 1/3, so we need to find f of negative 1 by 3. And again, I'm just going to use the calculator. It's totally done. So what I'm going to do here, I'm going to show what I'm doing here. So first, I'm using a TI-83 plus. I'm going to go to my y equals. I'm going to just type in the original 3x to the power of 4 minus 4x to the power of 3 minus 6x squared plus 12x plus 1. Okay? So then I'm going to go back to my main menu. I'm going to go to, you see the button to the right, it says clear. To the left of that, it says variables. I'm going to click that. I'm going to go to Y variables. Number 1, number 1. So now when x is a negative 1 by 3, we get our corresponding y. I'm going to say this is approximately negative 3.48. And then we also need to test, and that's going to be, so that's an inflection point. It goes from concave down to concave, sorry, it goes from concave up to concave down. And then let's do f of 1. So I'm just going to recall, and I want to leave just the 1. 6. Okay. So we have inflection points at negative 1/3, comma 3.48, and we have another one at 1,6. Okay, this is what I got as far as inflection points. Nope. Oh my goodness, you are bugging. Give me a moment. Okay. Somehow it got knocked off, whatever I was just doing. Okay, reload and refresh. All right, so I guess we got to type all that back in. 3x to the power of 4 minus 4x to the power of 3 minus 6x squared plus 12x plus 1. Variables, y variables. Oops. y1 of negative 1 by 3. So we got last time approximately 3.48, and then I think it was f of 1 was 6. So we have inflection points at negative 1 by 3, comma whatever, negative 3.48, and at the point 1, comma 6. Let's see, how do we do? Okay. All right. Negative 1/3 and 1. Yeah, I'm just not gonna do the second one. I'm kind of tired. Okay, when x is -1/3 and when x is 1, those are inflection points. Okay. So let's see. The second derivative test. Suppose f double prime is continuous on an open interval with f primacy equal to 0. F double prime being positive. So we've identified f prime is equal to 0. If the second derivative is positive, then f is going to be, if it's positive, that means it's concave up. It should be a local minimum. If the second derivative is negative, that means it's concave down, and we're at a local maximum. If f double prime is 0, the test is inconclusive. It still may have a local max or a local min. Okay. I think I'm not gonna do that one. Second derivative. All right, I'm gonna leave the rest of these as exercises. Okay. You should be able to handle it. If you need me to go through these, just let me know, and I will. Let's look at this recap really quickly, and we're gonna close out here. So, say we have f is differentiable on an interval and f is a smooth curve. Then let's see, if the derivative is positive, then we say that the function is increasing. If the first derivative is negative, we say the function is decreasing. If the first derivative changes from positive to negative or negative to positive, then we have a local max or a local minimum respectively, right? So if it goes from positive to negative, that means we would have a local max. If it goes from negative to positive, that means we have a local minimum. If the first derivative is 0 and the second derivative is negative, second derivative being negative means that it's concave down, means we have a local max. If the first derivative is 0 and the second derivative is positive, that means it's concave up, which means we have a local minimum. The second derivative is positive, means that it's concave up. Second derivative is negative, means that it's concave down. And if the second derivative changes from positive to negative, that means it goes from concave up to concave down. Then we have what's called a point of inflection. Okay. All right. Let me see. I can't really think of anything else there. Okay. I'll go like this. Aside from, like I said earlier, we're entering the home stretch of everything. I do want to get into chapter 5 somewhat, so we'll stop somewhere in chapter 5. I do want to at least mention intervals. Intervals is the other half of calculus that's like made really important. We just, we'll see what the time is like, okay? But we're going to keep going with chapter 4. On Moodle, be sure that you've completed the participation and honesty quiz, and also there is an assessment that's available. You get 1 attempt. I think it's timed. So just do the best you can. It is for a grade, but it's not a heavy part of your grade. It's going to be factored in as a quiz grade. Okay, on that note, we're going to end the session here, and from one beautiful mind to another, enjoy the rest of your day. Peace.